Greetings and welcome back. Today we'll be looking at free radical reactions, or reactions that involve electrons moving one at a time instead of in a pair. In class, we've been looking at the propagation step of a free radical reaction. Propagation. And the propagation is the reaction in which we start with our radical, whatever it is. And in case of free radical halogenation, which we focused on in class recently, that would be like a halogen radical. And we could pull the hydrogen off of a carbon by reacting one electron from bromine, which needs a second electron. And the easiest one to pull off is one of the electrons from a CH bond. Well, that would give us a brand new bond between bromine and hydrogen. But any bond has two electrons, and if you take one away, you have one electron remaining, and that electron would go over to that carbon and be sad all by itself. So every propagation step involves an unpaired electron ripping apart a bond to make it self-stable, but that always leaves behind an unpaired electron in its wake. So now the reactive species is this carbon radical. And normally what happens in the second step of propagation, at least in terms of free radical halogenation, is that that carbon radical does the exact same thing. It would rip apart a Br2 bond, making a brand new bond to one of those bromines, but leaving the other bromine behind as a bromine radical. So that would give us a C attached to a bromine. That's my new bond. Yay! And we would also have a bromine radical. Sorry, guy. That's left by itself. And then that bromine radical would basically come back up here. It's the same thing. That could rip apart a CH bond, and that would make a new carbon radical, which would rip apart a Br2 bond and make another bromine radical that would rip apart a CH bond and make a new carbon radical that would rip apart a Br bond and make a new bromine radical. But you'll notice that overall what's really changing is that we are going from an alkane to an alkyl halide. So that's propagation, in that this cycle propagates. It goes over and over and over again, and we end up making the same things over and over. We turn a radical and a stable bond into a new stable bond, but a new radical. And that radical rips apart a stable bond, giving us a new stable bond, but then also a radical, etc., etc., etc. And of course, the CH that you tear apart is always determined by which of those intermediate carbon radicals is the most stable. Because a carbon radical doesn't have enough electrons, it follows the same rules as a C+, which doesn't have enough electrons. So it's more stable with carbon neighbors, it's more stable with resonance, etc. So what I'd like to do is move into how we make those initial radicals. And the way that this happens is by a step called initiation. So what happens at the beginning to make that radical? There are 4 different common ways of doing this, and we'll go through them one at a time. But let's start with the simplest, which is that if you start with 2 halogens, like a Br2, you can add light. Light is often indicated as H nu, which is Planck's constant, times frequency, which is the equation for the energy of a photon. But basically that just means it's a fancy way of saying light. What light does is it causes Br2 to break homolytically, meaning evenly, into 2 bromine radicals. You might ask yourself, well, why don't those radicals just get back together? And you're right. That is something that would be certainly a stable thing to do. Except that once they break apart into radicals, it's not a bucket full of radicals. They tend to be dissolved in a solution, and they tend to lose sight of each other. If they got back together again, that would be called a termination reaction, but it's very hard for that to happen just based on sheer chance. There's really low concentrations of these bromine ions, and the chances of them finding each other are very slim. So that's our first way to do initiation. We can make a bromine radical by just simply breaking apart a Br2 bond. Another way of doing this involves peroxides. Peroxides in either light or heat can break apart in the exact same way. Both of those oxygens pull really hard on electrons. They're very electronegative, just like halogens are. So those bonds can be broken exactly in half, which will give you oxygen radicals. Oxygen radicals are also very common, and what they will want to do is the exact same thing that Br radicals will want to do, which is to break apart a stable happy bond. You may recall from last semester that we had a reaction in which we added HBr and peroxide, and what will happen is that first you'll break apart those peroxides, and then those peroxides will want to rip apart some HBr. So just like we saw in the last slide, the oxygen radical can rip off that hydrogen, making itself a brand new bond. Yay! But unfortunately, this bond had 2 electrons, and if you take one away, you end up making a bromine radical. So you would make a neutral alcohol, which is great for that alcohol, because now it's all neutral and everybody has a nice stable bond, but you make a bromine radical as well. So notice that we get to the exact same point that we did by breaking up Br2, except that in this case we didn't have to add any Br2, we added peroxides and HBr. All right, the third way of doing this is a much better way. It involves NBS, which is N-bromosuccinimide. Succinimide looks like this. It's a 5-membered ring with a nitrogen and 2 carbonyls, so it's kind of like a double amide. N-bromo means you have a bromine attached to the nitrogen. So this is N-bromosuccinimide. And if you use either light or heat, you can break this guy apart. And this bond is easy to break. It again will be broken in half. And what we would get out of this guy is that you would have an N with a radical and a bromine with a radical. So you might notice that it's kind of similar to the very first one, that we make a bromine radical, and we're in pretty good shape. However, in this case, this guy doesn't really stop here. What we find is that that bromine radical then can go ahead and do propagation and make some HBr, but when we have that HBr, it will of course like to split into H plus and Br minus. The way that we form the HBr is on the last slide. That's a main part of propagation. That's what our bromines turn into. And then that Br minus and H plus can react with another molecule of NBS. You can protonate one of those oxygens, which would give you an O plus up there, which is a really good electrophile, which would want to pull these electrons up to the O and pull these electrons over towards that carbon, meaning that the nitrogen is effectively a good leaving group, meaning that that bromine is a pretty good electrophile, and the other bromide can attack, and so therefore, at the end of all of these shenanigans, we would make an OH up here, double bond N there, and some new Br2. So the only reason we got some more Br2 is that we made the Br minus. And if you kind of think about this in terms of what we do with propagation, every time that we allow one of these bromine radicals to take apart a CH, which is what the bromine radicals do, we generate a carbon radical, but we also get our HBr. And the HBr that we just made allows us to get another molecule of Br2, which would then react with another carbon radical and make a Br radical, and that will pull a hydrogen off and let us make another Br2. So essentially the advantage of NBS is that it does the exact same thing as Br2 in light, but you don't actually add in any Br2. And that's really important sometimes because Br2 can do some other reactions. So in effect, using NBS, the whole goal of this is it keeps a low but steady concentration of Br2. So if you don't want to add Br2 because Br2 can react with something else, then we can use NBS instead. It does the exact same reaction, free radical halogenation, except that it always keeps your amount of Br2 very low. In fact, it only generates a Br2 when you do the reaction once. So instead of having piles of it around, you just keep a low and steady concentration of Br2. So NBS is effectively the best way of doing free radical halogenation. So these three methods right here can all be used to generate a halogen radical, which can be used in initiation. There's a fourth way, or a fourth pretty common way of generating a radical, but it's not a halogen radical. So this initiation would not be good for carrying out your free radical halogenation, but it is very good for some other methods, therefore I'm going to present it to you right now. So AIBN, which is isobutyronitride, which I don't expect you to in any way be able to draw that, so I'll draw it for you. Boom, boom, boom. CN, that's the nitro part. N2, that's the azo part. Isobutyr. Well, sorry, those are triple bond ends in both cases. So this is AIBN, and AIBN is a very common free radical initiator. The way that this works is that there's a reversible reaction. All of these free radical reactions are reversible, but we can take one electron from each of those CN bonds to make an N triple bond N in the middle. It would cause the other electrons to move to the center of that species, and that would look kind of like this. So you would have a radical that is tertiary and has resonance, which is a pretty good way for a carbon radical to be, and you would generate N2, which is a gas, which bubbles off. And therefore, this reaction is actually irreversible, because the gas would bubble out of your solution and be gone. Those two radicals can't get back together because they're so crowded, and therefore you end up making radicals that can facilitate any type of propagation or free radical reaction. So AIBN is just a really good way of making radicals. We use that a lot in making polymers, which we'll talk about next time. But for now, these are 4 different ways to carry out initiation reactions. And initiation reactions all start with stable happy bonds, like Br2, or a radical, or NBS, or this AIBN. None of those things have radical, or have radicals, but when we break them apart, which in this case is heat, in all the rest of these cases you can use light for them, but none of them are very hard to break apart, but when we do, they only break homolytically, which is to say that bonds break in half, making radicals. The radicals that we make can be a halogen radical, or an oxygen radical that gives you a halogen radical, or a different halogen radical, or in this case, a funky carbon radical. All right, thank you very much, and I will see you in class.